Hi everybody, this is Mr. Short. Today we're going to be talking about electron configurations and relating electron configurations and Bohr models to the periodic table. Now a couple times throughout these lessons today, I'm going to be flipping back and forth between these notes and a periodic table and some previous notes that we've already taken, so you might want to have these out as well. To start out with, we have to get a better understanding of what the term valence electron means, what valence electrons are and why they're important. So valence electrons are the electrons that are located in the outermost energy level in the Bohr atomic models. So this is energy level. So energy level in the Bohr atomic model. Okay, that would be the ring in the Bohr atomic model that's the biggest ring. It's farthest from the center. So again, valence electrons are located farthest from the nucleus. The reason valence electrons are important is because they're the ones that participate in forming chemical bonds, and also they participate in chemical reactions as well. So guiding question, how many valence electrons can an atom or an ion have? Atoms or ions can have this magic number 8. They can have up to 8 valence electrons. All right, we're going to take a look at the periodic table in just a minute and get a better understanding for why that is. Guiding question, how can you tell by looking at the periodic table how many valence electrons an element has? You can tell how many valence electrons an atom has by looking at its main group number, by taking a look at its main group number on the periodic table. Now the saying for main groups is 1, 2, skip a few, 3, 4, 5, 6, 7, 8. Let's flip over to the periodic table and get an understanding for why that's the saying. So again, the main groups are 1, 2, skip a few, 3, 4, 5, 6, 7, 8. Okay, so what that means is if an element is in main group 1, anything from hydrogen all the way down to francium, all of these elements will have one lonely valence electron. One electron that's located in the outermost energy level. Similarly, anything in main group 2 will have 2 valence electrons. We skip this central sunken down region, that's the skip a few section. Anything in main group 3 has 3 valence electrons. Anything in main group 7 would have 7 valence electrons, and anything here would have 8 valence electrons. So again, main groups are the column numbers, they're the vertical columns, and the saying to remember this is 1, 2, skip a few, 3, 4, 5, 6, 7, 8. Let's check that and make sure that we understand why based on this picture that's right here. So for example, here's a picture of neon. You can see that neon in its Bohr model, it has 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. It's these 2 valence electrons plus these 6 valence electrons. And confirm that neon is over here in main group 8, so it should in fact have 8 valence electrons. Likewise, here's a Bohr atomic model for germanium. You can easily count 1, 2, 3, 4 valence electrons in germanium. It's these 2 valence electrons plus these 2 valence electrons right here. Remember, these are not valence electrons because this adds 10 electrons to this crowded third energy level. So 1, 2, 3, 4. It's these 2 plus these 2. Germanium has 4 valence electrons, and in fact, here is germanium right here in main group 4, vertical column 4. Okay, if we go back over here, I want you to write the word columns in here. Okay, so note that columns are main groups. Main groups are vertical columns found on the periodic table. Okay, what happens to valence electrons when an atom turns into an ion? So I want to remind you, in the last unit, section 1.1, we learned that when atoms turn into ions, they gain or lose electrons, never protons. But now we're going to expand upon that definition, so just keep that in mind. When atoms turn into ions, they will gain or lose the fewest number of valence electrons possible, so that they have what's called a stable octet of 8 valence electrons. So remember, in the last unit we said that when atoms turn turn into ions, they gain or lose electrons, never protons. Now we're expanding that definition and saying when atoms turn into ions, they'll gain or lose the fewest number possible, fewest number of valence electrons possible, so that they have what's called a stable octet of 8 valence electrons. Okay? So down here you'll see that there's a periodic table. And what you'll need to do is either digitally write in or maybe hand write in. If you're taking these notes by hand, you're going to write the charges above the 8 main groups that atoms in the 8 main groups take when they turn into ions. Now I've already done this. All I need to do is to go like this, and I'm going to change the text color. And what you're going to see is that if we apply this description up here for how atoms turn into ions, along with our definition for the number of valence electrons in any element in the 8 main groups, that it's going to lead us to these conclusions. That atoms, when they take these charges and turn into ions, they're going to take those particular charges. Okay, for example, if we're talking about any element in main group 1, they would have 1 valence electron. Well, they want to gain or lose the fewest number of valence electrons possible to get to this stable octet of 8 valence electrons. There are 2 ways for it to get to 8 valence electrons. Since they have 1, they could either gain 7 valence electrons or they could lose 1, but they're going to do the fewest. Because they do the fewest, they're going to lose 1, taking a +1 charge. Okay, another example. If you take a look at the element aluminum right here, this would be aluminum. Aluminum really likes to take a +3 charge because, since it's in main group 3, it has 3 valence electrons. Its choice is to either gain 5 valence electrons or lose 3 valence electrons. And see how the 2 numbers that I just listed add up to 8. Let me say it again. It can either gain 5 or lose 3. 5 and 3 is 8. Well, it does whichever number is smallest. It's going to lose 3 electrons, so it's going to take a +3 charge. Let's talk about an anion, something with a negative charge over here. Oxygen is right here. Oxygen loves to take a -2 charge. This main group right here is main group 6. Elements in main group 6 can either gain 2 or lose 6 to get to a stable octet of 8. They're always going to gain 2 because that's the fewest. And remember, by gaining 2 electrons, it takes a -2 charge, not a +2 charge. Okay, so what charge do the group 8 noble gases take and why? Well, if you take a look up here, we've got the number 0 above column 8. So this is main group 8, 1, 2, skip a few, 3, 4, 5, 6, 7, 8. They take no charge. And if we think about this statement up here, it makes sense. Elements in main group 8, because they've already got 8 valence electrons, they've already got a stable octet of 8 valence electrons, so they don't need to gain or lose anything. And so for that reason, they're going to take 0 charge or no charge. So the group 8 noble gases do not take a charge because they already have a stable octet of 8 valence electrons. And this makes them unreactive, and another word for unreactive is inert. Now, if we have any students in the welding class or maybe in the auto technology class, you might know that you have argon gas that you keep inside your lab for the purposes of welding. The reason that you keep argon gas in there when you weld is because if you inject a weld with argon gas is a group 8 noble gas. It's right down here. It doesn't want to react with anything, including the iron that you're welding. And so what you can do is inject the weld with argon gas. That keeps oxygen out of that weld, and it makes it a much stronger weld, less likely to oxidize and fail over time. All right, last guiding question. We already know that the main groups tell you the number of valence electrons. That's 1, 2, skip a few, 3, 4, 5, 6, 7, 8. So we also might want to know about the period number. What information does the horizontal period number tell you about the Bohr atomic model? So the horizontal period number tells you the number of energy levels. Tells you the number of energy levels in that Bohr atomic model. Let me make this red real quick and then I'll show you. So the horizontal period numbers are like this. Here's period 1, period 2, period 3, period 4, all the way down to period 7. Okay, let's flip over to this one and take a look. Here, we've got neon. 1s2, 2s2, 2p6 is neon. I want to go and show you that neon is right over here. Neon is in horizontal row or horizontal period 2, telling us that it's going to have 2 energy levels. And in fact, you can see it does have 2 energy levels. Here I can easily count 1, 2, 3, 4 energy levels for germanium. So we could make a prediction that germanium is going to be in horizontal period 4. So if we count down 4 periods, 1, 2, 3, 4, here is germanium right over here. So the horizontal period number tells you the number of energy levels in the Bohr atomic model, whereas the vertical main group number, the column number 1, 2, skip a few, 3, 4, 5, 6, 7, 8, tells you the number of valence electrons in the neutral atom. Okay, that's the end of lesson number 1 here, and in just a minute I'll post lesson number 2. Thanks.